So we're going to talk about water potential in today's discussion and how that influences the movement of water or osmosis. The key idea before we get too far in talking about water potential is that water is always going to move from higher value water potential regions toward lower value water potential regions. We're going to see that Greek letter psi quite a bit to represent overall water potential. And so you're still thinking, say, of inside and outside of a cell. And if you're able to calculate or estimate what the water potential values might be, then you can predict which way the water will move. So we're going to, just as a brief example, we're going to often see that water potential values might be negative. So just a reminder that negative numbers, sort of the bigger the negative number, the lower in value it is. So what if I were to calculate the water potentials for both inside and the outside to be this? Then we would find that negative 5 is greater in value than negative 24. So we would predict that the water would net move into the cell by osmosis from higher value, negative 5, water potential to lower value water potential. Okay? So another way of starting to think about an application of this main rule is we're going to see that there are really pulling forces and pushing forces in water potential. And so it makes sense to maybe think about any force that would pull on water would make the water want to come toward it. So if we made that water potential value negative in value, that makes sense that we're lowering its value, and so we're perhaps incentivizing water to come toward it. Whereas perhaps on the other hand, it makes sense for any kind of pushing force. It makes sense for us to make that maybe positive in value, because if we're pushing water away, by making it a really high positive value, then the water would perhaps move towards some other region. So we'll see examples of both of those here very briefly. The way to calculate water potential, this equation is actually given on the AP Biology equation sheet, so you just have to be able to know how to apply it. The idea is that the overall water potential in any region is controlled by two factors. One of these we're very familiar with, and that's psi s. Psi s is really just a solute potential again, so it's the factor how solute controls how water moves. But psi p is really something we haven't considered yet. Psi p is going to be, sometimes this is what's referred to on the equation sheet as pressure potential. And really, you can think of that as being like physical pressure. Physical pushes and pulls and how that might influence water's movement as well. And so what we do with this equation is we say that if we're really going to think about which way water moves, we need to think about both of those contributions by adding them together in our overall thoughts. So let's start perhaps with the topic we're a little more familiar with based on our last conversation about water's movement. Solute can influence water's movement, as we've seen, and all we're going to do is try and make this mathematical in our approach. So we have arbitrarily called pure water to have 0 bars of pressure in this kind of mathematical scheme. So it has 0 bars of pressure, and since solute always pulls water towards it, there is no particle that dissolves in water that pushes water the other way. Since solute always pulls, we're going to start with 0 bars of pressure for pure water, and we're just going to say that as we add more and more solute to a region, we want to make that region more and more negative in solute potential value. Because the more solute you add to a region, the more water should rush to come into that region. So let's make it lower in value. Let's make it more negative. Right? So if we were to apply this briefly to a situation we saw in the other video, we already know perhaps from the other video that we could call this inner region hypertonic to the outside. And we know that generally water follows the solute absent a physical force. And so if that were the situation here, we might predict that water would net move into the cell. right? Well, we could do the same exact thing with water potential calculations. If I were just to make up numbers for water potential that makes sense in this case, I could say that outside the cell, the overall water potential is controlled by its solute potential and its physical pressure, or pressure potential. Let's go ahead and just assume that this is 0 for now, that it's not playing a role, and I'll talk more about the role of physical pressure here in just a little bit. If I were to make up a value, there's at least some solute outside of this cell, so let's just kind of call it a value of, say, -10 bars of pressure. If this seems totally random, that I'm just making up values, I'll give you a more formal way for calculating water potential in just a minute, or solute potential. But for the most part in my course, as long as I might just ask you to do a broad analysis where you can kind of make up numbers that make sense. And all I want to convince you of is that inside the cell, we're going to want that solute potential value to be more negative because there's more solute in there. So if I were to make up something like, say, -15 bars of pressure, then if that really is just the overall water potential, because physical pressure isn't playing a role, then we've once again predicted that the water will net move into the cell from a higher value water potential, -10, to a lower value water potential, -15. Okay. Now there is a more precise way of calculating this again. So let's just briefly go through the formula. We might practice a few calculations in class. This is also given on the equation sheet for any kind of AP test calculations. And this isn't really that important a formula to work with, in my opinion. But we'll briefly go through it. The way to actually calculate how much solute is pulling in a given region is really controlled by different factors. I is called the ionization constant. So does the solute particle that we're considering ionize? If, for example, I were to add a mole of sodium chloride into my solution, sodium chloride salt will actually break up upon entering water and really form a mole of sodium ions and then also another mole of chloride ions. So yeah, I originally added 1 mole of sodium chloride salt, but it's effectively become 2 moles of solute particles because it formed 2 ions after hitting the water. And so the ionization constant is you just want to sort of have a multiplying factor in your calculation that factors in how many ions form upon putting the salt into your solution. So for example, NaCl would have an I value of 2. If something doesn't ionize at all, like say sugar or sucrose, it doesn't turn into different ions upon hitting water. We would just give it an I of 1 so 1 times anything would just be itself. So we're not really changing the overall calculation. Okay, that's I. C is simply concentration. How concentrated is the solute solution that you're adding? So this is often just given in terms of molar. So 1 molar sucrose would just be 1 mole per liter. That's the same thing. And so oftentimes we'll report our concentrations in molars. R is just the gas constant that you might remember from chemistry class. R is will be given to you on your equation sheet, so you will never need to memorize R. But R is simply 0.083131, and the units are a little strange, but they're liter bars over mole kelvins. So that's a very strange unit, but basically that's going to work so that every other unit cancels out. Liters from concentration, moles from concentration, and Kelvin from temperature. Temperature is our final variable, and temperature is simply what is the temperature. It is important that this be in Kelvin according to our gas constant, but your equation sheet will remind you how to calculate the temperature in Kelvin. It's just 273 plus whatever the degrees are in Celsius, which is what I would give you in any kind of question. So if I were just to briefly apply all of this in a sample question, we'll do this in class as well. And if we were to actually calculate how much pole does a 0.5 molar solution of sucrose have at room temperature, then we could use our equation. Negative ICRT. Remember that it's also negative. I don't know if I emphasized that on the last slide, because remember that the greater the pole here, we want to indicate a pole with that negative sign, with that negative value. So what would this be in this case? Remember that sucrose does not ionize, so I would simply be 1. We're going to multiply that by its concentration, 0.5 moles per liter, or molar. We're going to multiply that by the gas constant, 0.0831, and that's in liter bars per mole Kelvin. And then we're going to multiply that by 25 Celsius, and 25 Celsius, you have to add 273 to that, is simply going to be 298 Kelvin. Kelvins cancel on top and on bottom. Moles cancel, numerator, denominator. Liters cancel, denominator, numerator. And what are we left with? We're left with our units of pressure, which is what water potential is in. So if I were to calculate all that out on my calculator, which you would certainly have for any kind of calculation like this, we would find that it would actually have about negative 12 bars of pressure. Again, I probably won't have you do this very much at all, and for the most part you can just make up values that make sense. Okay, so we've discussed solute potential a little bit, and we've discussed how the solute can perhaps pull on the water and make it come to a certain region. Just like we discussed before, if physical pressure is not playing any kind of role, then the greater the solute concentration in a certain area, the more it's pulling water to come towards it. Okay, but physical pressure can also play a role, and we need to add that into our consideration if it is present. We're not going to have a calculation for Sci-P, so we're just going to talk about it more generically and just about the broad idea of the concept. I'll also try and introduce some areas where we're going to actually see physical pressure play a role in the movement of water and living organisms. But for our purposes, it can either be a push or a pull. For example, if you imagine me having a water balloon in my hands, and if I were to squeeze on one end of the water balloon, it might sort of push the water away from where I'm squeezing and sort of bulge out in the area opposite it. So it makes sense to have the push be a very positive value, because generally when I push on water, I'm making it go away from my push to a different area. Pulls are also possible with physical pressure. In this case, maybe think of a syringe. If I drew up on the syringe, what I'm actually doing is creating kind of a negative tension pressure, and the water comes toward it because we're going to represent that with a very negative value. Just like solute can pull, so can tension pressure forces. Okay, so it can be a push or a pull, and then the other thing to consider is that if a system is ever just at atmospheric pressure, if I'm thinking of, say, a plant cell in a cup, and the cup is just open to the atmosphere, and I surround it with a solution of some kind, then the outside solution can just be said to be at 0 bars physical pressure. It's just at atmospheric pressure. There's no additional push or pull being exerted on the system, so we can just call that 0. Where are we going to see Sci-P play any kind of role? We're going to see it play a role as a pushing force in turgor pressure with any kind of cell that has a cell wall. For example, plants. So if I were to imagine solute being in this cell, come on, pen. If I were to imagine some solute being as solute is present in any cell, then if I had pure water outside, in the outside region, then the psi s outside would be 0 because it's pure water. The psi s inside would be something negative, say maybe -5 with the solute that's in there. So you might predict, if you were just to use solute potential alone, that water would always rush in. But at some point the water stops coming in because eventually the cell might get stretched enough that the cell wall pushes back. And if the cell wall pushes with a positive Sci-P pressure, and if it pushes back just as hard as the solute pulls, then we add these values together and we find that the psi inside is 0, just like the psi outside is. Remember that the psi p outside would also be 0 if it were at atmospheric pressure. And what happens when the water potential values are equal is we predict no more water movement really net either in or out. So the plant cell could actually reach equilibrium even in a pure water situation because the cell wall is pushing back. The other place where we're going to see psi p play a role in terms of a negative tension pressure is transpirational pull. And in fact, that's pretty much the next topic we're going to move to in Chapter 36. And we're going to see that when hydrogen bonds break, when water molecules escape out the plant in transpiration, when they go from liquid to gas form, they're essentially going to pull the rest of the water up in a kind of tensional, very negative psi p force. And so we'll talk about that more when we get to Chapter 36. So this is the overall equation. We're not going to do much with psi p. We're going to talk about it in some brief cases. But as long as you get the overall picture of this equation and how it relates to water movement, that's the goal of our talk today. So just in brief summary, we're interested in you knowing how water potential predicts water movement. It's always moving from high to low values. In the case of calculating psi s, we will actually provide you with equations to do that. You just have to know how to use them. And in most cases, you can kind of make up values that make sense. The solute potential could potentially be 0 or something negative. Solute potential can never be positive because solutes never push, whereas physical pressure could potentially be positive, negative, or 0 if there's no additional pushes or pulls other than atmospheric pressure.